I'm now going to do a more complicated scenario. We're going to use implicit differentiation to find y prime, which is the derivative of y with respect to x, of sine of y plus x to the third equals 12 minus y. Here's our function, sine of y plus x to the third equals 12 minus y. I misspoke. This is not a function, but it's going to yield a graph. So we're going to take the derivative with respect to x of both the left-hand side and the right-hand side. Now, when you take the derivative of the left-hand side, this sine has derivative, which is cosine. Be careful about this. Cosine of y times y prime, right? Y here is the inside function, so that's what we're doing. When I take the derivative of x to the third, there's no inside function. X is just the inside function, so we can add 3x squared. The derivative of 12 is 0. The derivative of minus y, well, normally it'd be just -1, but since y is an inside function, it's -1 times y prime. I have to, again, multiply times the derivative of the inside function. Some people will just write this as -1 y prime. In order, going forward, what we have to do is we have to solve for y prime. That's going to mean we need to get our y primes on the same side. So what I'm going to do is I'm going to take cosine y times y prime, leave it on the left, and then I'm going to add 1 y prime to both sides. If I add 1 y prime to the right-hand side, I get 0. If I add 1 y prime to the left-hand side, that goes on the left. Then what I can do is I can subtract 3x squared from both sides. So I end up with cosine y times y prime plus 1 y prime equals -3x squared. After that, the left-hand side, I am going to factor out a y prime. So since y prime is multiplied times both terms on the left, we can take y prime times cosine of y plus 1 equals -3x squared. And then for my last step, I just divide by this cosine y plus 1. So we end up with y prime is equal to a fraction, which is -3x squared divided by cosine of y plus 1. Again, that's not an explicit derivative for any x, but if I know a point on that graph, then I can plug it in here and figure out what the slope of the tangent line is at that particular point. So that's the technique, is to use the chain rule, viewing y as an inside function, and then try to get all the y primes on the one side, factor it out, and then divide. Let's go ahead and do another example. In this example, we're going to find the derivative, the y prime, using implicit differentiation, and we're going to find that of this equation, 5x squared times y to the third plus 9x to the sixth equals 100. Here's the equation of our whatever the graph happens to be. I don't actually know what it is at this point, but we can figure it out. So 5x to the squared, y to the third, plus 9x to the sixth equals 100. Now, before I do this through implicit differentiation, I do want to mention this one is solvable for y, but if you solve this for y, it's going to be a pretty hot mess of a function. If you solve this for y, you would get y to the third equals, it would be a fraction of 100 minus 9x to the sixth divided by 5x squared. And then you could take a third root of both sides. So you'd have to take a 1/3 root of that fraction. And you can imagine how difficult it would be to find the derivative using all of those rules that we dealt with in the previous sections. So instead, let's use implicit differentiation. Take a derivative with respect to x of the left-hand side, and then take a derivative with respect to x of the right-hand side. Note that we're taking derivative with respect to x. So we have two pieces here. Taking a derivative with respect to x of 9x to the sixth, that's pretty easy. Taking a derivative of 5x squared times y to the third, well, that piece involves a product of two functions, namely 5x squared and the function y to the third. And it involves a chain rule because y to the third is going to take into account a chain rule. So that one can be a little bit tricky. So let's go do that. Derivative of 5x squared is going to be 10x. We're going to multiply that times the normal second function. The normal second function is just y to the third. So we're not taking a derivative of y to the third now. We're taking a derivative of the first part. Plus normal first function, that's 5x squared, times derivative of the second function. Derivative of y to the third is 3y squared times y prime. Plus, now take a derivative of 9x to the sixth. That's going to simply be 54x to the fifth. Derivative of 100 is 0. So you can see that this one is a pretty involved equation. We can clean that up a bit, make our lives a little bit easier. 5x squared times 3y squared is going to be 15x squared y squared. So now what I'm going to do is solve for y prime. There's only one term with a y prime on it, so I'm going to leave that term on the left. And the other terms, I'm going to move to the right by subtracting 10xy to the third and subtracting 54x to the fifth. And then I can solve by dividing by the coefficient of y prime. We are going to get a big ugly fraction, 10xy to the third minus 54x to the fifth, all divided by 15x squared y squared. So if we start with this equation here, we get a graph, which could be transferred into a function, but it turns out that it's much easier to do implicit differentiation. I knew this took a lot of steps, but it turns out it's much fewer steps than if we were to solve for y first and then try to take the derivative explicitly. So that's how we take the derivatives of things like that. I would like you to try to use implicit differentiation to find the derivatives, the y primes, of the following two equations. So find the y prime given each of these two equations. Go ahead and push pause and do those on your own.